All right, so I am here audibly to have another go at creating this screencast for our multiple choice questions. Depending on which class you're in, we may or may not have gone over some of these ourselves. So let's go ahead and get started. So I've got two flexible containers, so that means their volumes can change if they're flexible at the same temperature and pressure. Well, if they're at the same temperature and pressure, they must have the same average kinetic energy if they're at the same temperature. One holds 14 grams of nitrogen, the other holds 22 grams of carbon dioxide. Well, how many moles is what's going to influence the volume or the pressure, not the number of grams. Grams could influence the density, but it's not going to influence your volume. It's not going to influence the pressure. You got to be looking at moles. So to figure out what these amounts would be in moles, check out the molar masses of these gases on the periodic table. Nitrogen's diatomic N2. Each one's 14. 14 times 2 is 28. So 1 mole of nitrogen would have a mass of 28 grams. I don't have 28 grams. I have 14. 14 is a half of 28, so I must have a half a mole of nitrogen. Now you could do that with a bracket, but on the multiple choice you're not going to have time. Now 22 grams of carbon dioxide. The formula for carbon dioxide is CO2. Oh, sorry. I know everyone's looking at my hand maybe. I cut it. Yeah, hopefully just don't look too close at it. Anyway, so I need to get the molar mass of this. So 16 times 2 is 32. 32 and 12 makes 44. So the mass of 1 mole of carbon dioxide is going to be 44. I've got 22 grams, so I don't have a mole. I have a half a mole again. So I've got a half a mole of nitrogen, and I got a half a mole of carbon dioxide. All right, well, if the moles are equal and the temperature is equal and the pressure is equal, then the volume would also be equal. All right, let's take a look. It says, which of the following statements about these gas samples is true? The volume of the CO2 is yes. Let's look at the others just to show why they're not right. The number of molecules in CO2 container is greater? No, they have the same number of moles, so they'll have the same number of molecules. The density of the sample is the same? No, density is mass over volume. So even though the volumes were the same, the masses of nitrogen and CO2 are different, so the densities would not be the same. The average kinetic energy are different? No. If they're at the same temperature, they have to have the same average kinetic energy. The average speed of the carbon dioxide is greater than the average speed of nitrogen? Nope. CO2 is 44 grams per mole. Nitrogen is 28. Nitrogen is lighter, so its average speed is going to be greater. Okay, let's go to number 2. A sample of 0.01 moles of nitrogen dioxide gas, nitrogen dioxide is NO2, dioxide, is confined, that means it's sealed, at this temperature, which I am immediately going to convert to Kelvin. Add 273, that gives you 400 Kelvin. What would be the pressure of this sample at 27? So you'd add 273 to that, and that will give you 300. So it says the volume is kept constant. So I don't need to worry about that. Since it's sealed, the number of moles is going to be constant. So all that's changing here is the temperature. And the temperature went down from 400 to 300. So it went down by a factor of 4/3 or 1 1/3, 1.33. Now, what's the relationship between temperature and pressure? If the temperature drops, the molecules are going to move more slowly, they're going to collide less often, and with less force, so the pressure is going to drop. By how much? By a factor of 1.33. So you would take 2.5 atmospheres, and since it needs to drop by this factor, I'm going to divide it by 1.33. Now, I'm going to round here. 2.5 is around 2.6. This is around 1.3. 2.6 divided by 1.3, that's going to give me 1.88, give or take. Let's go to number 3. So we've got a hydrocarbon. That means it's made out of hydrogen and carbon with the empirical formula, that means simplest formula, CH2. We're told that it has a density of 1.3 grams per liter. That means there's 1.3 grams for every 1 liter at 0 degrees Celsius and 1 atmosphere. Now these, and you need to recognize this, are standard temperature and pressure. When you are at standard temperature and pressure, 1 mole is equivalent or will occupy 22.4 liters of space. What do they want to know? A possible formula. If I'm going to identify the formula of material, a great way to do that is if you can calculate the molar mass. Molar mass is grams over moles. So what do I know already? I know the mass, 1.3 grams. What I don't know right now is my number of moles, but I do have my volume, 1 liter. And I know that 1 mole occupies these many liters at standard temperature and pressure. Okay? So if I just have 1 liter, that means I've got 1/22.4 of a mole, because 1 mole would be 22.4. I only have 1 liter. 1 liter is 1/22.4 of a mole. Now, when you divide by a fraction, it's the same as multiplying by the reciprocal of that fraction. So I'm going to take 1 times 22 is 22. 0.3 times 22 is 6.6. Add those two babies up, you're going to get around 29. And if you find the molar mass of each one of these, this guy is 14, 24, and 4. This one's 28. Ooh, that's really close to what we got. That has to be our answer. Let's go to number 4. A real gas would act most ideal. So what does it mean to be ideal? Remember, they occupy no space in the container and have no attractive or experience no attractive or repulsive forces. Now, the only way you can get that to occur is if the molecules are moving super fast. So you want high temperature. So I'm going to cross out this, this, and this. Now, if I want the gas molecules to be occupying no volume in the container, I want an enormous container, which means I want very little pressure pushing on it, because high pressure would jam everything together. I don't want that, all right? That would make for lots of attractive repulsive forces, so I want a low pressure right here. So if you want to, memorize that. Real gases behave most ideal at high temperature and low pressure. I explained why, but memorize it. All right, number 5. The reaction below takes place in a closed, rigid vessel. So if it's rigid, the volume's constant and cannot change. If it's closed, that means nothing can escape. I see this word initial. The initial pressure of N2 is, and then it gives me another material. When it says initial, I start getting suspicious that I might need to be doing an ice table. The fact that it gives me the amounts of both of my materials confirms it. So I'm going to write these in. The initial amount of nitrogen gas is 1 atmosphere, of oxygen gas is 1.5. There isn't any of this to start. The experiment is carried out at a constant temperature. Okay, great. What is the total pressure in the container when the partial pressure of N2O4 reaches 0.75? So if the N2O4 reaches 0.75, it must have gained 0.75 atmospheres of pressure. Well, if he gained that much, how much did we lose of our ingredients? Now, the changes always have to reflect the ratios in the balanced equation. So if you look at the ratio between oxygen and N2O4, it's 2 to 1. That means you're going to lose twice as much oxygen as you did of this stuff. 0.75 times 2 is 1.5. So it looks like we are going to run out of oxygen. So it must be what we call our limiting reactant. Now, how much nitrogen will I lose? Not that much in terms of the oxygen. This is a coefficient of 1 and he is a 2. So the nitrogen is only going to lose 1/2 of 1.5, so 0.75. Notice how these two changes are the same, just like their coefficients in the reaction are the same. So that'll finish 1 minus 0.75 is 0.25. What did they ask? What is the total pressure in the container? 0.75 plus 0.25 is 1 atmosphere. Coming down here to number 6. A 0.33 mole sample of calcium carbonate is placed in a 1 liter evacuated flask. So they gave us the volume. Evacuated means there was nothing in there. It's empty, which is then sealed and heated, or I mean empty besides what I've put in there. The calcium carbonate decomposes completely according to the balanced equation. This is going to be a very important word, completely. Look for that. According to the balanced equation. It says that it's already balanced, so I don't need to go through here and balance it. The total pressure in the flask measured at 300 Kelvin is closest to which of the following? The fact that they gave you the ideal gas constant tells me I'm probably going to be looking at using the ideal gas law. More on that here in a minute. I've got an issue. This is not a gas. This is not a gas. This is the only thing that's a gas. So this is the only thing that's going to be contributing to the pressure. And initially, there wasn't any of it there. It said we had 0.33 moles of this stuff, calcium carbonate. What did it tell us, though? It said it decomposed completely. So minus everything, 0.33, to give you nothing left over at equilibrium. So how much calcium oxide are you going to produce? Look at the ratios, 1 to 1. So the same amount I lost here, I'm going to gain here. Not like I care too much, because he is a solid and will not be influencing the pressure. Now the carbon dioxide also has a coefficient of 1, so I'm going to gain 0.33 moles of him. Okay. Now, since he's the only thing that is contributing to the pressure, this is what I'm going to use as my number of moles in the ideal gas law. It wants the total pressure. So I'm going to say PV equals nRT, divide both sides by V, P equals nRT over V. And we're going to have to put these numbers in. So 0.33 moles times 0.0821 liters atmospheres over moles Kelvin. Notice how I'm not taking any shortcuts. It's good to practice your units. Times the temperature, which is 300 Kelvin, divided by the volume. All right, now they told us the volume up here was 1 liter. So now we do need to do our math here. It actually works out pretty easy. 0.33 is the same as 1/3. 300 divided by 3 is 100. So you're just going to take 100 times 0.0821. Moves you 2 decimal places over, and you get 8.1. All right, now I'm going to pause the screencast and continue as soon as I have figured out where I need to go next. Okay, so I am kicking this back into gear, starting with question number 23. The temperature of a sample of an ideal gas confined in a 2-liter container was raised from 27 to 77. Again, immediately convert those to Kelvin. So I added 273. I'm going to do the same here. I can also picture, I know this is 50 higher than this, so this is going to be 350 Kelvin. If the final pressure was 1200, if the initial pressure was 1200, what was the final pressure? Well, we're assuming that the temperature was the only thing that changed, that the volume in the moles did not. We can safely assume that. It says it's confined, so it's sealed. So how much did my temperature go up? It went up from 300 to 350. So that's a factor of, just simplifying this, of 7/6. All right, so that's only 1 1/6. So 1 1/6. So that's a really small, increase. So I would not expect a big increase in my pressure. So 1400. 24. A sealed container containing 8 grams of oxygen gas, O2. Now I'm going to reflexively convert this to moles because I know it's moles that influences many of these characteristics of a gas. So the mass of 1 mole of oxygen, 16 times 2 is 32. I only have 8 grams, not 32. So 32 would be 1 mole. 8 grams is 1/4 of that. So I'm going to have 0.25 moles of oxygen. And 7 grams of nitrogen gas. Well, nitrogen is N2. If I have 7 grams of that, the mass of this is 28. So I definitely don't have a mole. Now, 7 out of 28, that's 1/4. So it looks like I also have the same number of moles of nitrogen. So I have the same moles of oxygen as I do the nitrogen. So if their moles are the same, the temperature is the same, and the pressure is the same, and it says that they are, so moles, temperature, and pressure all the same, then the volumes must be the same. So that's out, and that looks good. All right, the volumes would be equal. Okay, let's take a look at number 25. A gas sample contains 0.1 moles of oxygen and 0.4 moles of nitrogen. If the sample is at standard temperature and pressure, what's the partial pressure due to the nitrogen? Well, standard temperature and pressure. Standard pressure is 1 atmosphere. Okay? Now, to find out the partial pressure of a gas, it's proportional to the number of moles of the gas. And if you remember back from Unit 2, Lesson 17, if I ever want the partial pressure of a gas, take the total pressure, which is 1 atmosphere, and multiply it by the mole fraction. In this case of nitrogen, so there's 0.4 moles of nitrogen for every total number of moles. 0.4 and 0.1 is 0.5. So what on earth is 1 times 0.4 over 0.5? Well, 0.4 over 0.5, I can just ignore the decimals. 4/5 is 0.8, or 8/10. Times 1, 8/10. Easy. Easy, easy. 26. A mixture of gases contains 1.5 moles of oxygen, 3 moles of nitrogen, half a mole of water vapor. How nice of them to give it all in moles instead of grams that we would have to convert. If the total pressure is 700, what is the partial pressure of the nitrogen? You handle this one exactly the same way that you handle number 25. So you should have no problems with it. All right, and then check the answer at the back of this sheet that's attached. Okay. 27. A mixture of helium and neon gases has a total pressure of 1.2 atmospheres. All right, so I have a mixture of helium and neon together has a pressure of 1.2 atm. It says, if the mixture contains twice as many moles of helium as neon, what is the partial pressure due to neon? All right, so I'm going to put these in moles. I'm going to call helium X. I'm going to call neon then, wait, what is it? Twice as many moles of helium. All right, so I'm going to make neon X moles. Helium, I'm going to make 2X moles. Okay? And if I want to know the partial pressure of neon, it's going to be equal to the total pressure, which was given for you, 1.2 atm, times the mole fraction of neon. So this is multiplication times the mole fraction, which is going to be X moles over X plus 2X. To combine the two, that would be your grand total, all right, of your number of moles. So you'd have 1.2 atm times by, so X plus 2X, that's 1X plus 2X is 3X. So you'd have X over 3X. These cross out, 1/3. So you'd have 1/3 of 1.2, or 1.2 divided by 3. That's 0.4. All right, still got some problems left to do. I've got to pause it. All right, continuing on here. So this time I'm collecting gas over water. Now I know I worked through some of these with one of the classes, so one of the two classes might not need to be looking at these because we already did them, but I'm going to put them up on the screencast anyway. So nitrogen gas was collected over water at 25 degrees Celsius. Whenever you collect a gas over water, going back to Unit 2, Lesson 17, you're going to have a container that you collected gas in. The gas is going to be up here. But mixed in with it, you're going to have some water vapor that evaporated into that container. So the pressure up here is going to be what we call the wet gas. And if the water level in here is the same as this, the pressure of the wet gas in here must equal the pressure pushing down on it outside, which is atmospheric pressure. Now they gave us the total atmospheric pressure as 781 millimeters of mercury. So that must be the pressure of my wet gas. To get the pressure of the dry gas, or just the gas that you wanted to collect, you have to get rid of the water vapor pressure, which was given to you as 23 millimeters of mercury. So subtract those two, I get 51 and 758, so 758 right here. Okay, number 29. When 4 moles of oxygen are confined in a 24-liter vessel at 176, the pressure is 6 atmospheres. If the oxygen is allowed to expand isothermally, to expand isothermally means that the temperature will not change. Iso means the same or equal, thermal, heat, temperature, etc. So it's allowed to expand, so the volume is going to get bigger from 24 to 36. What's the new pressure? Well, if the volume is expanding, that means that there's going to be fewer collisions over that area. So you're going to see a drop in pressure equivalent to the increase here. So how much did the volume go up? By a factor of 36 over 24. So the pressure will go down by that same factor. The pressure was originally 6 atmospheres. So it's going to go down by this much. So I'm going to divide by 36 over 24. When I divide by that fraction, it's the same as multiplying by the reciprocal. Watch how easy the math is. 6 and 36 becomes 1/6. 24 divided by 6 is 4. And we're done. A gas sample is confined in a 5-liter container. Which of the following will occur if the temperature of the container is increased? Well, temperature measures the average kinetic energy. So if you speed molecules up,
I did not get offered a second, so that's okay. I just want to let you.
okay, so if you have I got my gas confined into this container, so which of the following will occur if the temperature of the container is increased? Now we're going to assume that this container is rigid, which means its volume cannot change. That's what we're going to assume about it. All right, they really should have said that, but we're going to assume it's a rigid container. So if you crank up the temperature, the kinetic energy will definitely increase. I mean, that's what the temperature is. It's a measure of the average kinetic energy. Now, if the volume can't change and the molecules start moving faster, you're going to get more collisions, and they will be more forceful, so the pressure is going to rise as well. Now, the density is not going to be able to be affected. Remember, density is mass over volume. Neither of these can change in a sealed, rigid container. You can't change the mass if no one can get out or in, and you can't change the volume if it's rigid. So there's no way the density can increase. So just 1 and 2. All right? Okay. Number 31. A 14-gram sample of an unknown gas occupies 11.2 liters at standard temperature and pressure. Which of the following could be the identity of the gas? Whenever you want to know the identity of a gas, calculate the molar mass, which, as we've done many times, is grams over moles. We know the grams are 14.0 grams. So how many moles? Well, when I'm at standard temperature and pressure, I know that 1 mole of a gas occupies 22.4 liters. I only have 11.2 liters, so I don't have a mole. In fact, I have exactly a half a mole. So I'm going to be taking 14 divided by a half, which is the same as 14 times 2 over 1, which is 28. So I want to look to see which one of these has a mass of 28. Nitrogen is 2 nitrogens makes 28. 1 carbon is 12. 2 oxygens, that's 32, and 12 is 44. That ain't right. So I like nitrogens, 28, supposed to be 28. This guy, 12 and 16, that's 28, that's a keeper. So these two could be the identity of the gas because they both have a molar mass equal to what we calculated. So what is that, 1 and 3? Number 32. Consider the combustion of 6 grams of ethane. What volume of carbon dioxide will be formed at standard temperature and pressure? Now, this is an old question because they used to require students to know these formulas. All right. Now, the formula for ethane is C2H6. Okay, that's going to be important. It says, what volume of carbon dioxide will be formed at standard temperature and pressure? This is also handy. 1 mole of any gas will occupy 22.4 liters. So if I want to know the liters of carbon dioxide, looks like I can get it if I know my number of moles of carbon dioxide. And I know I can get moles of carbon dioxide if I know my number of grams of carbon dioxide. All right? And I can get there from the ethane. Now, this is going to be interesting. It'll push you a little bit. The first thing I'm going to do is write a balanced reaction. There's the formula for ethane. When something burns or combusts, it's reacting with oxygen. The two things that are going to be produced here are carbon dioxide and water. Whenever you burn a hydrocarbon, you will make carbon dioxide and water. To balance it, 2 carbons, I'm going to need 2 here. 6 hydrogens, I need a 3 times 2 will give me 6. What's my number of oxygens? 4 and 3 is 7, so I need 7 halves here. All right, cool. Now, I do have my ratio, though, of my ethane to carbon dioxide. It's 1 to 2. That's going to be nice to know, okay? I'm going to start off with my 6 grams of ethane. And I'm looking at my plan, and I'm going to want to get grams of carbon dioxide. So I'm going to do that from grams of ethane. This is easy. Carbon dioxide, carbon's 12, oxygen's 32. With the two of them, 12 and 32 makes 44. But I make 2 carbon dioxides for every one of these. So I'm going to double that 44 and make it 88. Ethane, I just have one of them reacting, so I just need to add everything up. 24 and 6 is 30. Ooh, I like that math. 6 goes into 35 times, so this would be 1/5. So what I really got is 88 divided by 5. Okay? But I'm not done because I know I need moles and liters of CO2. Notice I label everything. That's going to help you a lot. Carbon dioxide, for every 1 mole of it, there's a mass of 44 grams. 88 over 44 is 2 over 1. So this is working out nicely. Now my number of liters per mole, we know since we're at STP that 1 mole will always occupy that 22.4 liters. So where am I at? I'm going to be taking 2 times 22.4, which is around 44, divided by 5. That looks to be right around 9. And there it is. Notice I didn't have to do any long division, but I needed to do a lot of figuring. There's no way you're going to be able to look at any of these and just be like, that's the answer. All right? Nobody does that. Number 34. Which of the following conditions would be most likely to cause the ideal gas laws to fail? To assume we're ideal means we assume that the gas occupies no volume, and we assume that there are no attractive and repulsive forces. Well, those conditions are most likely at high temp and low pressure for these conditions to be met. All right, I'm back. Sorry, I have to keep pausing. People coming in and out. All right, a gaseous mixture at a constant temperature contains oxygen, carbon dioxide, and helium. Which of the following lists the 3 gases in order of increasing average molecular speed? Well, we know that the molecular speed is proportional to their mass. So oxygen has a mass of 32, carbon dioxide 44, helium is 4. Just knowing those saves you a lot of time. So the fastest is going to be helium. So I can cross off these. And then oxygen's less massive than CO2, so this has to be the right answer. All right, 34. Maybe this is where I was at. So which of the following conditions is most likely to cause the ideal gas laws to fail? To be ideal, you need no volume, no attractive repulsive forces. And that's most likely at temperature, high temp and low pressure. Now that's for ideal. If I want those laws to fail, and I want the gases to have attractive and repulsive forces, and I want them to occupy a large amount of their container, aka I want them to be real, I want just the opposite of this. I'd want a low temperature so the molecules can easily form some attractions, and I would want a high pressure because I'd want to jam everyone next to each other so they would be forced to form some attractions and repulsions. So high pressure we would want, high temperature we wouldn't, large volume would allow the gas molecules to essentially have a negligible amount of that space that they're taking up. So I'm going to say 1 only. Now, If they're saying the large volume of the container compared to the size of the gas, that's how I'm taking it. But if it's a large volume of the gas itself, then you would pick these two, but they should really specify that. 35. An ideal gas contained in a 5-liter chamber at a temperature of 37, which I will immediately convert to Kelvin. 310 Kelvin. If the gas exerts a pressure of 2 atmospheres, which of the following is equal to the number of moles? Well, I can use the ideal gas law to do that. PV over RT is equal to your number of moles. So my pressure and my volume are going to need to be on top. So 2 atmospheres is the pressure, there's the volume. So this is a possibility. This is not, this is not, this is not, and this could be. So what is the difference between these two? This one has the temperature in Celsius. This is in Kelvin. It must be in Kelvin. A sample of 18 grams of aluminum metal is added to excess hydrochloric acid. The volume of hydrogen gas produced at 0 degrees Celsius in 1 atmosphere. Well, this is standard temperature and pressure, STP. So I know that 1 mole of any gas will occupy 22.4 liters at STP. So that's going to be helpful. So if I want the volume of hydrogen, liters, what I just need is the moles of hydrogen. Hydrogen's diatomic, H2. I can get that from my grams of aluminum metal, but I need a reaction. And you guys aren't at the point yet where you would know how to, develop this, but we're going to learn a little bit. If you take a metal and you put it in an acid, you're going to learn that the business end of an acid is H+. You'll make hydrogen gas. And what's happening is the H+ is gaining an electron to become 0 charge. And the aluminum is going to get oxidized. He's going to lose electrons to become aluminum 3+. Okay? Now, I can balance this by looking at my electrons. So if he goes from, he's 0 here to 3+, that's a loss of 3. The hydrogen, there are 2 of them here, so I have to put a 2 here. Each one gained 1 electron. 2 of them did it, so I'm gaining 2. Well, 2 and 3 both go into 6. So I'm going to need to multiply this by 3 to make this 6. Losing 3, I need to double that and that. And I am in business. All right. So I now have my ratio of aluminum to hydrogen, which I needed because they gave us the grams of aluminum to start. So let's set it up. I'm going to go to moles of aluminum. I know students often want to have an absolute. They're like, this is what you always do in this circumstance, and just be taught some set procedures, and that's not how it works. You've got to decide what's the right tool to use based on what your situation is and what you've been given. So I'm going to go from moles of aluminum to the gas that I want, which is hydrogen gas. And I can do that from moles to moles because I have my ratio. So for every 2 moles of aluminum, I'll make 3 moles of hydrogen gas. Now, they wanted liters. Now, I know if I'm at STP that 1 mole of any gas occupies 22.4 liters. So now, hopefully, we can simplify the math quite a bit, and we can. I can divide both of these by 9, and I get 2/3. I can now cross off my 3's. I can cross off my 2's, and I just get 22.4. Pretty cool. All right, so you're seeing the amount of work that goes into getting these problems correct. I'm going to save 37 for 43 or through 43, and I'll post them up tomorrow, probably tomorrow morning. My prep is fourth period. I think I'll do it then. But I've got to go, so I'm going to shut down the screencast.